It's a pleasure to have Jay Sau virtually with us for this colloquium. And so Jay did his PhD at Berkeley with Marvin Cohen, and after that he sort of switched his fields and came to CMTC as a postdoc, where he wrote an influential paper which Microsoft liked so much they spent a lot of money on it subsequently. And then after that, Jay moved to Harvard and continued his work on that subject and among many other things. And then after that, he came back to Maryland as an assistant professor, where right now he's tenured as a faculty there. So Jay has vast interests, as you can see, switching from more ab initio-based systems to topological quantum computation. And so it's a really, and this talk will probably reflect that diverse interest in many things. So thanks, Jay, for coming, and so it's all yours now.
All right. Thanks, Sharam, for the invitation. Yeah, this is. I wish I could actually visit you guys in person. That's what I was. Telling my wife. I mean, going to New York would have been fun, but oh well. Yeah, but at least I get to talk to you guys. So yeah, thanks. So today I'll be telling you about sort of a long-standing interest of mine at this point on Majorana particles and the possibility of topological quantum computation. And yeah, and as you might have guessed from Shriram's introduction, that despite my wide-ranging interest in condensed matter theory and electron structure, I mean, this search for Majorana has occupied at least half my time over the past 10 years or so. And it's, as much as I want to leave it, it continues to bug me, and partly because, so out of my support over that time, I had listed this Q. It's nothing ominous. It's Microsoft Station Q. And that's the branch of Microsoft research that supports quantum computation and topological quantum computation. And they really got interested. Well, they were interested in topological quantum computation since 2005, actually starting with fractional quantum Hall that I'll talk about. But then since 2010, they have been interested in this platform, which I will describe. So the motivation for what I'll tell you goes back to topological states, and the notion of topological states and Majorana fermions, both of which are actually rather fascinating notions in quantum condensed matter physics that have been around since, well, topological states since the 80s, and then there was a Nobel Prize for it in 2016, and Majorana fermions since the 90s. So, well, actually, Majorana's Majorana fermion has been around since the 30s. So they go back a long way. So let me start by first telling you a bit about what topological states are and why we are so excited about it. An example of a topological state would be, at least experimentally, is the so-called fractional quantum Hall system, where you take a two-dimensional, you take a gas of electrons, confine it to 2 dimensions, like, for example, in a quantum well, gallium arsenide quantum well, you apply a magnetic field on it, and the first observation is that you get what's called the Hall conductance becomes quantized. And that's a nice manifestation of Landau levels. But then the next thing that that was noticed was that sometimes these the quantized Hall states can also occur at fractional values, which is sort of, it feels like it's sort of contradicting the quantization. But when people thought about this more deeply theoretically, they realized that the system must be effectively described by excitations with fractional charges. So even though the system was made of electrons, the excitations in the system, which in a cartoon I'm trying to show is depicted so, would have like one E/3 charge or E/4 charge or so on and so forth. So 1/3 or 1/4 the charge of electrons, and so there'd be like some kind of soliton. And so that's interesting, and people have seen preliminary evidence for this. But actually, what's the most dramatic feature is that if we manage to wrap this electron gas around a torus in some way, and this is of course not practical experimentally, well, almost, at least so far, the lowest energy state of the system, the so-called ground state that condensed matter people focus on, that state would become degenerate, right? They would have the same energy. So there would be multiple states, multiple lowest energy states, all with exactly the same energy. And this is very special. This is very special for anyone who's seen quantum mechanics, because in quantum mechanics, usually the energy of a system depends on external perturbations. For example, if I have an electron sitting in free space, the spin can be up or down, and those states will be degenerate. But as soon as I have a magnetic field, one of the spins will become preferred, and this degeneracy will be broken. In this case, the degeneracy on a torus, one, depends on the topology of the torus, and secondly, does not depend on any external perturbation. Like I can apply magnetic field, I can apply electric fields. That degeneracy is not going to be lifted. Right? That's sort of, in the view of most condensed matter physicists, a very fascinating quantum concept we have had for a long time, and it's been developed in detail to the point that theorists are bored of it. But experimentally, we're still looking for this. Now, it was realized that Majorana fermions are a route to realizing this kind of degeneracy, even without putting the system on a torus. Sorry, actually, so the way this works is that certain filling fractions, so I told you certain fractions, turns out to be 5/2 is one of them, pi/2, they have a special state where these excitations, these Majorana fermions themselves, in some sense, act like the holes of the torus, and you get degeneracies even on a plane. The degeneracy depends on how many Majorana fermions you have. Moreover, Majorana fermions provide a way, this property of non-abelian statistics. So if I just had a bunch of states lying around, that's not terribly interesting unless we can manipulate the states. And it turns out that Majorana fermions have this property called non-abelian statistics. Again, I'll elucidate this. That lets you manipulate these states. There have been actually, I certainly did not come up with the first Majorana fermion proposal, or was not involved. These Majorana fermion ideas have been around since the 90s. The first ones were fractional quantum Hall from Moore and Reed. Then there were P-wave superconductors from Volovic and Reed and Green. Topological insulator-based proposals from Fu and Kane in 2009, and I'll come back to this a bit. But mostly I'll focus on a semiconductor superconductor-based proposal that I was involved in as part of my postdoc work in Maryland. And my excitement partly is that this was the first system where some evidence for the Majorana was seen in 2012. Though now more evidence is piling in, so we'll have to see which one, where more ultimately progress gets made. Now,
so you will be talking about
yes,
this experimental status, right? Eventually, so.
Oh, absolutely. No, that's going to be a large part of my talk.
Okay, I will wait for that. Okay.
Yeah, no, definitely. I can't go through all of it, but I'll go through as much as I can. Yeah. So, okay. So firstly, why why should not condensed matter people care about this? And the answer is quantum computation. And now I guess over the past few years, in terms of funding and everything, I think all of physics is going quantum computation, the way of quantum computation. So maybe this is, I mean, there's no, yeah, I probably don't need this slide anymore, but I'll regardless, just in case you missed this story. So the idea of quantum computation, again, I guess goes back to Feynman, though, from the 80s, though it wasn't until Shor's paper in 95 that, that this became a real thing to pursue. So the basic idea of a computer is to find two-state systems like light bulbs and or switches, and call refer to one of the states as 0 and the other state as 1. And then you take an array of a lot of these, and then you can represent numbers in binary 0 and 1 and do computation with them, like do math. A quantum, so on the other hand, if you, for physicists, quantum physicists like us, I mean, a natural thing to do is to then take superpositions, so a quantum analog of a light bulb, and put it in a superposition state of n1. And now we, in principle, have a much wider array of states, even though when we measure it, we're going to measure either 0 or 1. In principle, at least for some problems like factorization, this larger space provides an exponential speedup of computation. But in reality, I mean, of course, there's a reason we don't see quantum mechanics around us, which is that the environment, in a sense, decoheres a quantum state, this superposition, to send it back to either, makes it pick either a 0 or a 1. And the idea of topological quantum computation, which was a marriage of the idea of topological states and quantum computation, it was laid out by, in separate papers by Alexei Kitaev and Michael Friedman, was to make these light bulb states 0 and 1 out of topological states. And the idea was that if they are extremely robust to the point that you can't perturb them by a perturbation, then you might hope to avoid this decoherence. So again, I mean, I have been advised not to use this joke because it's been said too many times. But again, well, what is but I have to tell people, for those of you who are not familiar with topology by chance, so topology is a branch of math that deals with very robust properties of shapes. So the joke is that to a topologist, a donut and a coffee cup look the same because I can, if a coffee cup were made of rubber, I could stretch it and turn it into a donut. So basically, this handle of the coffee cup would become the whole of the donut, right? And an intuitive way to understand this robustness is if a property cares, if I store my qubit in how many holes this system has, then it would be robust to the perturbation of like wiggling this donut around, even if it were made of jelly. Now, an examples of phases, as I mentioned to you, were fractional quantum Hall systems and the vortices in P-wave superconductors. Now, let me also briefly tell you about, and again, these topological phases have quasi-particles in them that have weird quantum statistics. So, and that's what lets you manipulate these many-body states. So, so what do I mean by quantum statistics? So this goes back to another old sort of dogma from particle physics. Goes back to all the beginnings of particle physics in the 30s. So there are two kinds of quantum particles in particle physics: fermions and bosons. And so why only two kinds? Well, firstly, fermions and bosons are defined by what happens to their wave functions when you exchange them. So if I have a wave function for like some boson sitting at 1 and 2, if I exchange the particles, the wave function remains exactly the same, then it's a boson, like for a photon. And on the other hand, if the wave function flips its sign, then it's a fermion. But now here's the, so you can ask, why only fermions and bosons? Well, turns out that if I exchange twice in 3+1 dimensions, I have to come back to the same state. So which means that the wave function has to be invariant under doing this twice, which means that the sign is the only option. Now, it was realized at the end of the 70s and, oops, or the beginning of the 80s, that actually 2+1D is very different. If you take two particles, seen here, and you exchange them twice, and what I'm showing you here is a world line of two particles. This is what you would recognize as what people, or people like to do their hair would call a braid. You can't undo these two twists. This double twist is not identity. I mean, you can't undo it without having the particles bump into each other, which is equivalent to ripping the string. So you can't undo this. So which means that this, unlike 3+1 dimension, where there is no such braid, you don't have this spin statistics. So you don't have this, sorry, this two kinds, you're not limited by this two kinds of particles. And actually, you have a whole zoo of statistics that are possible in 2 dimensions. So we could have our usual bosons and fermions that we can have in 3D, of course. But you can also just get some phase. It turns out the phase is not a completely random number. I mean, ultimately, in theory, you have some constraints on it, but you can get a phase. And what was realized later, like towards the end of the 80s, is that you can actually get matrix. So this phase, so if you get a phase, the statistics is still abelian in the sense that if I interchange pairs of particles in different orders, I multiply by different phases, and ultimately the product of the phases commute. On the other hand, I can also get a matrix, in which case these exchanges won't commute, and these are called non-abelian statistics. So now what I get depends on the order. So this matrix vary phase defines non-abelian statistics, but when I get this, there's one more interesting feature. This wave function has an index, and this exchange process can't change the energy of the particles because the particles are not interacting. No energy is changing. So which means that all these psi k's must be completely degenerate. And that's the connection between topological degeneracy and statistics. Again, I'm going to try to make these clearer in the Majorana context because it's simpler in that context. But again,
Jay, there is
yes.
I have a question. So,
okay.
People generally, whenever they try to engineer these non-abelian states starting from abelian states, they always kind of are trying to put things on a higher genus surface, right? And that's where the degeneracy is inherited in some sense. So,
yes.
So if you think of an abelian state on a torus, for example, right?
Yeah.
It has a degeneracy.
Right.
So is the origin of that degeneracy is also similar to the non-abelian?
Yeah, that's actually a great question, and I mean, this was only realized. I think I want to credit my colleague Masan Barkashli for this. When this notion of parafermions. Well, he calls it genons, but
I think it was done
the
in Kitaev and Bravi paper in '98 actually on this
I see.
story called
Okay,
Mara.
fair
Some
enough.
part of it actually. Yeah.
Some part of, yeah, okay, but the point, yes, indeed, this abelian, the degeneracy, the non-abelian anyons, the degeneracy from the non-abelian anyons is not is related to the degeneracy of for abelian anyons on toruses, because in some sense these particles, these excitations of the non-abelian anion are like in a sense topological defects for the rest of the anions. So for example, the 5/2 state can be thought of as a superconductor of composite fermions, and the composite fermions themselves are abelian. They're actually they're fermions actually. They're not even non-trivial. They're fermions, but then the non-abelian anyons behave like vortices for these composite fermions. And those vortices are essentially like topological defects of the type, like they have a winding of the phase, and they're in a superconductor, they really behave like a stuck object, massive object. But in these non-abelian cases, though, these particles tend to be able to move. They're more mobile and actually like light. So unlike a defect in a hole in a torus, which is stuck, these things can actually move. And
I see.
yeah,
So,
and actually, right.
So you are basically having some access to these torus cycle operators, which are span the degenerate manifold.
Right.
Basically, the non-trivial cycles of the torus are somehow becoming dynamical in this construction.
Yeah, and actually one more point that I would want to make is that, sorry, and this is actually a point of contention in terminology that one of the pioneers in the field, Nick Reed from Yale, he really bothered people on. He really did not like the terminology Majorana fermions for the objects that I will talk about, for the reason that or Majorana particles, because his point was that the objects I'll talk about to a large extent are stuck. They are like the degeneracy of a hole around a torus. They don't move around, unlike the fractional quantum Hall Majorana fermions. So they're a little bit of a different object. Anyway.
Yeah.
All right.
Okay.
Great.
Thanks.
There are some
there is one question from David actually. Let me ask him. So David, go ahead, unmute yourself and ask your question.
Until David unmutes himself, can I follow up a little bit on Sriram's question? Non-abelian statistics exist also in 3+1 dimensions. They are parafermions and parabosons and further generalizations. They are based on non-abelian representations of the symmetric group. So they are not specific to 2+1 dimensions. It's just that they don't seem to be realized by anything useful in 3+1 dimensions, while in 2+1 you do realize them in these topological materials. Just as a point of principle that it's not only that in 2+1 dimensions you get non-abelian statistics.
I actually, and I am honestly not that's not the subject that I think about very much, even though, I mean, that is definitely an active part of condensed matter theory, but I just don't. So, but just to be clear, my understanding,
as a matter of principle, as a matter of theoretical principle, that non-abelian statistics do exist in 3+1 dimensions. They are not realized in nature because they don't belong to excitations of standard relativistic quantum field theories, and therefore they are not very useful concepts, but other than that, they do exist.
But are they associated with completely localized objects? My understanding was that there had to be some kind of string or etc. associated with the excitation for that.
They just invoke non-abelian representations of the symmetry group, so they don't need any string a priori. It's the
Oh, oh,
original
oh, oh.
parafermions that was a model before quarks became kind of more in fashion. The original
Hmm.
parafermions were called in to explain the statistical properties of nucleons. So, in that,
Okay, great. Thanks. Yeah.
okay, but
I'll
David is
do
talking without unmuting himself, so I profited from his silence.
this.
Yes. So let me see if I can unmute David. I cannot unmute him, but I can ask him to unmute. So David, I've asked you to unmute. Can you respond to that through your clicks?
Oh, there you go.
Yes, I'm asking you the following question. You treat all this wave function as point particle. As a matter of fact, even for the third, there is a particle in the vortex, which means some size dependent on the coordinate. So the question if it is restricted to some space, so we want to say R1 is R1 in some region, and separated. R1 and R2 are separated, otherwise they annihilate.
No, indeed. So let me clarify this. These equations are for go along with the set of assumptions that I didn't lay out. One is, so firstly, what are these coordinates? These are, of course, these are not the microscopic electrons, definitely. They're
Yes.
the wave functions of the whole system. And secondly, these coordinates, and so I'm assuming that the system is completely gapped. And these are the coordinates of the only allowed localized excitations in this system. And they're separated by more than the correlation length of this gapped wave function. So those are the assumptions. So a vortex actually, technically a vortex would not be allowed in this framework. We'd need to generalize the framework because the vortex is doesn't have an exponential decay length.
No, but a third.
A what, sorry?
A third is how you describe a third.
Means 1/3 excitation. I think that's what.
Yeah. Well, one-third excitations. I mean, the Laughlin state, for example, they are gapped, right? So they have a correlation length, and if they're separated by that correlation length, then if 1/3 excitation is separated by the correlation length, then I think this is okay, no?
Okay.
Yeah, maybe you can continue.
Yeah, we can come back to it.
Yeah.
Sorry, yeah, I'm going fairly slowly, but anyway, but this is good. This is good. This is actually a much more useful discussion. As long as I get to some of the experiment, I'll be happy.
Yeah.
So let me define. I'm still calling them Majorana fermions, but I'll clarify what I mean. So actually, what are my fermions? And again, this is to some of you are probably more experts, but I wanted to keep undergraduates in mind. So Dirac fermions by itself is a very fascinating story in the history of physics. I mean, just by, in some sense, almost pure thought, Dirac figured out that the relativistic description of electrons forced with consistency with quantum mechanics really required the introduction of positrons or holes. So these would be the antiparticle of the electrons. And these were indeed found, but Ettore Majorana was a young physicist at the time who was very bothered by this. So he thought hard about this and realized that, well, actually at that point he thought neutrons would be the candidate. But he realized that if a fermion did not have charge, then it was possible for the fermion to be its own antiparticle. So it could be the whole of itself. There was a way to write down Dirac theory in that way. And this was the advent of Majorana fermions. And actually Enrico Fermi thought of Majorana as kind of some kind of a genius at the level of Newton or Galileo, but he seemed to have some psychological issues. So I guess after writing this paper, almost in a letter, I think, to Fermi or something, he then got off on a boat and then disappeared. forever. So here actually I want to, I mean, this is an issue. So, okay, practically speaking, the property that, okay, sorry. So before, neutrons turned out to not be Majoranas because neutrons, once we understood enough of nuclear physics, it became clear that they couldn't be Majoranas. But and neutrinos still potentially could be Majorana, and this question still remains unclear. So what it means empirically for something to be a Majorana is that if a neutrino happened to be a Majorana, then it should be possible to take a pair of neutrinos and collide them and turn them into a pair of photons, which is just energy, some gauge field. Now, someone actually, asked me at the beginning, before this even started, then in some sense, photons are, well, trivially Majoranas, but usually people talk about this for fermions. Because fermions can't be, well, fermions are not bosons or excitations of a gauge field, typically. So now the object that we will talk about, and this needs some clarification, are what I call solid state emergent Majorana fermions, and I shouldn't even call them fermions, they're really modes. And this is because there are a couple of differences. So let me lay those out right at the beginning. So, sorry. Okay, now in condensed matter or solid state, the analogs of electrons and holes, ordinary Dirac fermions, can be defined simply in analogy with the quantum harmonic oscillator. So in quantum harmonic oscillator, so, okay, firstly, if it's a fermion, then there are only two states, n equals 0 and n equals 1. And if a system is its own, a creation operator for a fermion, just like an analogy with creation operator for a quantum harmonic oscillator, changes the number, increases the number from 0 to 1. And you can also have an annihilation operator, which is called a hole, which takes the occupation back from 1 to 0. So based on this, if particles and holes are related by Hermitian conjugation, then the Majorana is just an operator that is its own antiparticle. So gamma equals gamma dagger. If I apply this Majorana operator, once you go from, you occupy the state, and if I apply it again, then you remove the state. So these objects are really what we will call Majoranas. They're actually a little more specific than fermions, Majorana. In particular, they have a property that they're not really fermions, because fermions in this analogy behave like complex numbers, and I need a pair of Majoranas to write a fermion. So C dagger is gamma 1 plus I gamma 2, just right, I can write a complex number as a pair of real numbers. So what's weird about having Majorana fermions, or the existence of Majorana fermions, is that any fractionalized, even the fermionic state, which is just a two-level system, it's the smallest quantum system, appears to be fractionalized when I think in terms of Majorana fermions. So that's going to be my definition, and what I'll try to tell you is why it leads to some weird topological properties. All right, so now let me try to give you the cartoon for where the topological properties come from. So so what I'm showing you here is a cartoon of the kind of system I'll talk about. It's a one-dimensional system. It'll turn out to be a superconductor, which has, and let's assume and I'll explain why, that there are a pair of Majorana fermions at the two ends, gamma 1 and gamma 2. So I have to ask, what are the states, quantum states of the system? So to even define that, I need to define a complex fermionic operator, gamma 1 plus I gamma 2, And this operator, which is non-local, it's defined across the system. It doesn't have any local meaning. This can be either empty, and that's called the vacuum state, or filled. It's the quasi-particle state. N equals 0 or 1 are the lowest energy states with, okay, and then with fermion parity n, that's not terribly important, but the most physically relevant thing is the Majorana operators appear as toggle operators. So I can apply gamma 1 to the system and change this non-local variable n equals 0 from 0 to 1, and I can also change this operator by applying gamma 2. Now, now that this kind of tells us, it has a slight contradiction with locality, because I'm changing a non-local variable from two ends. Like I have a switch at two ends, and I can flip it from either end, like from flipping a light bulb from either end of a corridor. And if the two energy states have different energies, then actually what I can do is I can increase the energy by flipping it at one end and take that energy out by flipping it at the other end. So I would send energy instantaneously across the system, which is unphysical. So that tells me that these two states had better be degenerate if this situation can happen. So what this tells me is that as soon as I have Majorana fermions, I'll have some kind of protected degeneracy, which was what QUANTIZATIVE realized in 2000 and in the early 2000s. All right, so that's that's what I call Majorana zero modes and topological degeneracy. And not every Majorana fermion or Majorana particle will produce this. It has to satisfy the property gamma equals gamma dagger. So I'm running low on time, so I'll skip this. So Sriram, I nominally end at 5, but presumably you want to keep some of that time for questions, right? How long? When do you typically expect?
You can take 5 more minutes because we started late. So think of it as 5:10 or something where you can end, and like another sort of 20 minutes. Oh, sorry, 25 minutes.
Oh, okay, excellent. Okay, then I'll be less nervous about because I really haven't. I'm still way back in review, but again, those are the very important conceptual parts. So what I'm trying to tell you, so where I'm going to go next is what is the general scheme for creating these particles? Like what are the ingredients? What are the physical structure of the system? So there's one lesson that we learned from this story. A pair of Majorana fermions is a Dirac fermion. So I can't, as soon as whatever recipe I come up for creating a Majorana, if there is an extra degree of freedom, like a spin, then I'm in trouble. So in principle, I need to get rid of spin degree of freedom. The slide I skipped was basically to tell us that superconductivity is also essential. I mean, there are a few ways to get, there's only one way I know to get Majoranas, well, two ways, I guess. Well, one way only to get Majoranas without any form of superconductivity. But I think it's hiding somewhere, because the degree of freedom that represents that is hidden, that's protected by in this Majorana fermion, is ultimately just number of particles. It's 0 or 1. So unless I can create some huge uncertainty in the number of particles, that degree of freedom is not going to be protected from external electric field. So I need superconductivity of sorts. Now, so I need superconductivity and I need to get rid of spin. So the best way to do this is to take a semiconductor and apply a large magnetic field so that I spin polarize all the electrons in the superconductor, in the semiconductor. So I get rid of spin first. We don't know, okay, that mouse was really slow. We don't know any system of semiconductors which superconducts as well. These are hard to come by, though there are a few examples, but they're very restrictive. So the idea, our idea was to, well, just put the semiconductor next to a superconductor and hope that some superconductivity leaks over. But there's a problem. Most superconductors are made of Cooper pairs. So superconductors, again, for those of you who are not solid state physicists, are phases of matter where the electrons have paired up into Cooper pairs, and they're essentially bosons. But these bosons are usually spin singlet, so they have spin up and spin down, and they can't leak into a purely spin polarized semiconductor. So our solution was to then add spin orbit coupling, where the electrons, though being spin polarized, see a momentum dependent magnetic field. And so the spins can't, and now there is some projection for this process to be allowed, and we can get, in principle, this thing to work. So, so what this tells us is, well, first our ingredients have to be magnetic field, ZEEMAN field, superconductivity, and spin orbit coupling. And it also tells us that if we take a system without magnetic field, it would be non-topological, and we can get a topological transition by increasing ZEEMAN field from, or magnetic field from 0 to something finite in the system. So that would be another thing to look for, the phase transition. So so our first version of our system that we thought of, and this was again in my work as a postdoc almost 10 years ago, was to just put these things together: superconductor, semiconductor, and magnetic insulator to get the ZEEMAN field. But magnetic insulators are not very easy to come by. So in one dimension, we realized that we could replace the magnetic insulator by just a magnetic field. And when the magnetic field, so then we'd have a one-dimensional semiconductor wire, superconductor in a magnetic field. I would tune the Fermi energy, occupy the electron so that only one spin is occupied, and this is the band structure.
Jay, there is a question, is B less than B critical?
In this picture, magnetic field or B would be above B critical. So indeed, that's exactly, so we come up with this condition, the ZEEMAN splitting from the magnetic field was beyond this critical value. So really what's important is the ZEEMAN splitting from the magnetic field, not the magnetic field itself. And this depends on so-called the gyromagnetic ratio, which can be different in a semiconductor from 2. But when that happens, when it's bigger than square root delta square plus mu squared, this is just some analytic formula, we would get an end Majorana mode. This Majorana mode has 0 energy, so when we tunnel, we would see a 0 bias peak. Okay, so this was our prediction, and indeed, the magnetic field had to be greater than critical magnetic field. Yeah, that's a good question. And so now the question was, okay, so now what I'll talk about is, so what would be the basic signatures to look for? And then I'll tell you briefly about experiment versus some experiment and theory, and where, well, I'll work towards where we are. It's, I mean, I'm starting back at theory from 2010, so this is 10 years. So, and we still don't have a quantum computer, spoiler alert. Let's talk about what would be quantitative aspects of of signatures. So the first thing that I mentioned was there should be a topological phase transition. And what that means is if I measure the gap in the wire, in the middle of the wire somehow, the superconducting gap should close like so, and then reopen. And the value of the reopen field depends on the spin orbit coupling. So what I've plotted are various, and on the x-axis, I have magnetic, the ZEEMAN splitting from magnetic field. And when I go past a critical value, indeed, this is the Majorana phase here. And at that, after this, in this critical phase, which is now I'm plotting the conductance, the end conductance, is tunnel probe conductance, I should maybe see this gap closure. This is a little bit unclear. This varies from simulation to simulation, but then I should see a zero bias peak, conductance peak show up. And it turns out that this conductance peak, and I'll talk about this, is actually quantized at exactly 2e²/h. So that's, and this is actually strange. Independent of how high the tunnel barrier is, it's still quantized. So it's a topologically protected quantity. And so in principle, if we saw both of these coming together, this would be a good signature that people would believe. At least I think. So the good news is that 2 years after we made the prediction, some part of this was seen. So that in actually a few experiments, I'm only showing the one of the references, one of the data. And so the experiment is, this is an indium antimonide wire covered with superconductor, and then we're tunneling from the normal lead to the superconductor through the end Majorana and applying a magnetic field along the wire. If we do this, we see that above a certain magnetic field, you get a nice zero bias conductance peak in some devices, and you see something like a gap closure. What you don't see, and what is also is not inconsistent with the simulation here, is any signs of a gap reopening. And this has to do in the theory. I mean, the bulk gap is actually reopening in the theory. It's just that it's not accessible from the end. That's the problem. Now, there are a few other measurements that I'll tell you about a bit in a little bit, the 4-pi Jesusen effect and so on, which show other aspects of Majorana fermions. But so the good news is that you see zero bias conductance peak above critical field as critical magnetic field as predicted. Bad news is that you don't see the gap closure and reopening. So we need to look for more signatures. Now, this was a discussion that started right after the experiment and then has since then become bigger. It's at that point seemed a little bit alarmist, like climate change, like Al Gore sounded with climate change back in, like, I don't know, the 90s or 2000. And as time passed, it became more and more obvious that this is an issue. So here, some of the early papers from this 2012 paper sounded alarmist. So basically, the question was, does zero bias peak mean Majorana? And the answer was basically no. I won't dwell on it in the interest of time, but just to summarize it, if you have disorder, if you have a disordered superconductor in a magnetic field, you can randomly hit. There's a random chance of hitting zero bias peaks as you vary magnetic, as any parameter with some frequency, and then it becomes a quantitative question about, is the range of the zero bias peak good enough or large enough? And then this is an experiment where actually the data looks very much like this kind of zero bias peak. And then the other possibility was that something that actually bugged quantum, or is a big problem in quantum Hall as well, the potential at the end of the wire can lead to a situation where you have a slow, your bulk is non-topological, but you have a slow variation of parameters going out from non-topological phase to sort of vacuum phase or end, and you go through some topological phases in between, which are short. So that also produces sort of fake. So the bottom line of this conclusion is that there are ways of getting fake paired Majoranas. That's the crucial thing. In this case, the Majoranas will not be at the two ends of the system, but will be at the same end of the systems. And it's very kind of tricky to separate this. And this is unfortunately the state we are in at this point. So I'll dwell a bit more on this. So what can happen, and again, so we did some theory simulations, and when we raise the density of electrons with the increasing magnetic field, we see that there are subgap states in the superconductor called Andreev states. And as magnetic fields are increased, they can just cross, because you can imagine that one of this Andreev state has spin up, the other has spin down. The magnetic field is making them change in opposite direction, so they cross. And because of particle-hole symmetry, which is a fundamental symmetry of a superconductor, they tend to stick at zero depending on the parameters. And if I increase the chemical potential, and for reasons that I can't explain in detail here, they actually just end up completely sticking and looking like a lot like Majoranas, even though they're not Majoranas. A way to understand this is to look at this picture. This was, oh, this paper is, sorry, not on the archive anymore, but anyway, I forgot to update the reference. But in a true Majorana wire, so here's an example of a Majorana wire where I'm tunneling from the end, and this is a null barrier, and I'm really tunneling through one Majorana. I'm not tunneling to the other Majorana.
So JJ, Jufeng has a question. ABS can exist at B equal to 0.
Yeah, ABS can indeed also exist at B equals 0. So there's no critical, so the way to think about this is just imagine like a part of the semiconductor that's not completely covered by the superconductor. There can be a bound state there, which is spending very little time in the superconductor, so its energy is below the superconducting gap.
The conductor of the peak should be E squared over H, and it has not been seen in an experiment.
Yes, no, I am coming to that as well. It's 2E squared over
So
H.
What's the situation now?
Yeah, I'm coming to that. That will be 3 slides later. It's actually a very messy situation, unfortunately. So okay. But what I'm trying to tell you also is that that might itself also not completely resolve the situation, because these Andreev bound states or quasi-Majoranas, one of the ways that they can arise is by 2 copies of topological superconductors. If the ZEEMAN field is too large, then they can be split enough so that these 2 Majoranas don't talk to each other very much, but one still couples strongly to the lead, other couples weakly to the lead, and you see conductance only from one. So these are scenarios that we have to sort of distinguish or separate out. And now I come to David's question, what about conductance quantization of Majoranas? That would, well, as I said, it's not necessarily unique, but it would be very constraining. First, let me tell you a bit of theory, which I'm, again, in interest of time, I'm really not going to spend a lot of time on. But it's sort of beautiful, so that's why I wrote down some of the equations. The bottom line is, so if I think about the conductance into a Majorana, it's really a reflection problem of electrons through the Majorana and from the superconductor. So electrons in the normal lead reflect, and they're reflecting by this matrix. They have a special symmetry called particle symmetry, and that constrains the conductance. And that's what leads to this constraint of quantization. And actually, if I had a spin polarized channel, then, spin polarized, if my barrier were, spin polarized channel from the normal lead, then actually, then I only have 2 options. The non-topological phase would give me 0 conductance, and the topological will give me 2e squared by h conductance, and then this is a smoking gun. For a spinful channel, I can get any answer from 0 to 4 for non-topological, and for topological, I would get 2. So in principle, I can get 2 by accident even in a non-topological phase if I have spin. So that's the thing to look out for. Unless I can get rid of spin, I have to worry, did I get the 2e squared by h by accident? Okay, so with that being said, now let's look at a little bit of data. So I told you that,
excuse me, can I mention to
yes.
you a theory of an experiment of two coupled chain, a chain which is superconducting, coupled to two rings which is metallic, and you inject injects electron on one side, and you obtain an electron hole, and this is really like a effect
Cross under reflection, yes.
Yeah, I can give you the reference of the paper. Have a look. So
okay, yeah. Sure.
So this was 2019 Journal of Physics 21.
Yeah, maybe at the end of the talk we can
What?
Yeah, please send it to me in the chat.
Oh, in chat as well.
Or email me. Yeah, that would even be better. Yeah, that would even be better.
This is actually a proposal for a quantum device, which is based on my Andrea cross reflection. You have two zero modes, Majorana at the edge of the wire, contact the ring, and then you manipulate the flux with the injection of electrons.
Okay. Yeah.
Okay,
that sounds. Yeah, I'd appreciate it.
You understand the picture, yeah?
Yeah. You're right. You're actually I'll talk about that device a bit, I think. Well, or that kind of device a little bit, I think. Though I guess actually even this system, yeah, it's actually close to the device that I'm showing here. So this is again from Delft. And what I want to say is that, this is paper from 2018. This device is actually a result of a substantial experimental effort. And this is where Microsoft's investment came in. They figured out how to deposit the aluminum in an epitaxial way so that it has at least some amount of very little crystalline defects relative to the crystalline nanowires.
Sorry, I have a class.
You have a class?
Yeah.
Oh, that's unfortunate. I see.
Yeah, you can send an email, David. So we will be happy to answer you. Yeah.
Right.
Yeah. Okay. Yeah. Continue.
But in any case, in this device, actually some amount of quantization was seen. So if you look at the conductance as a function of magnetic field, it reaches near quantization. And actually another device from Copenhagen, which is the Charlie Marcus group, also connected with Microsoft, also reached near quantization. And what you see is that at low temperatures, the conductance has very little dependence on tunnel barrier, which is also a good sign. But unfortunately, actually, what is not the quantization. Well, the quantization on the right plot is not very quantized. On the left plot, it looks quantized, but this turns out to be a little bit of an artifact. So these are close to quantized, but not very. And for quantum computation, actually, precise quantization is very important. Okay. So maybe, yeah, so I'm running even lower on time, so I will probably, unfortunately, speed up a bit more.
You can take 7 minutes more.
Okay. All right, good. Thanks. Yeah, I'll still speed up a bit. Thanks. So, but what I want to say is that there are, since then, actually, a lot of other Majorana platforms have cropped up. So one example was based on, surprisingly, on the proposal of Fu and Kane on topological insulators. This proposal actually predated the semiconductor wire proposal from Maryland. And actually this proposal served as some kind of an inspiration. But experimentally, this turned out to be relatively challenging to pursue. until this magic material showed up, iron, tellurium, selenium superconductors. I mean, the material was around, but what was realized that for a small range of doping, this material could be a topological insulator in the bulk. And indeed, and then you have a situation where you have a surface state of a topological insulator and a bulk superconductor from the same material. And then the prediction is that when you have a vortex in this superconductor, you would have a Majorana mode that you can tunnel into with the scanning tunneling microscope. And this was seen, and actually this shows very nice quantized conductance. Okay, this is the weird part. Only 2 of the vortices out of like 20 show quantization, but nobody shows more than quantization. So it's a intriguing avenue. Now, what I want to talk about a bit more is what about other signatures for Majoranas? Is there some way to be sure that we have Majoranas? And so the answer is going to be not clear, but let me basically let me make one point. So what are we looking for? Based on this Andreev story that I told you, it's very easy for pairs of Majoranas to masquerade as Majoranas, and this is a very important distinction for quantum computation. So we need some way of understanding that the bulk properties have changed, not just the end. So one idea proposed was to actually look at a little bit like the setup that David was alluding to, transport of electrons across the wire itself. And what you would see there you necessarily measure the bulk gap, because the only way for an electron to go all the way across is for the bulk gap to close. And so you get a bulk gap closing and reopening. And this is the theory plot. Unfortunately, this experiment was also done, it just appeared on the archive this year, so it's very new. And this shows a bulk gap closing, which is encouraging, but not much of a reopening. And that's disappointing. So actually, incidentally, your neighbors, the Javad Shabani group at NYU found some supercurrent closing and reopening for the same kind of physics. But again, this is all we're still trying to understand. Now, so another very fascinating property of, actually defining property of topological phase, Majorana phase, is the so-called flux response. So I told you that an example of a Majorana topological superconductor would just be like a spin polarized superconductor. If I could pair them up into Cooper pairs in momentum space, this is what I would get. The interesting feature is that that state would have one electron that is unpaired at 0 momentum. If I introduce a pi flux for electrons, that phase shift would move away remove the electron at k equals 0, and I would now have an even number of electrons. So this superconductor, this topological superconductor, has a weird flux property. Firstly, it can have an odd number of electrons. Normal superconductors only have even number of electrons. And in addition, it changes with flux. And if you could check this would be a smoking gun in principle. And this is a bulk property. So there are some efforts to check this. But again, this has the same fate. So far we have some vague evidence for it, but we're still trying to figure this out.
So this is like an evidence for topological superconductivity, right?
Yeah, exactly. As opposed to Majorana fermions, this is direct evidence for topological superconductivity. And the advantage would be if you know it's a topological superconductor, you're guaranteed that there's a Majorana there, even if you didn't see the Majorana.
Okay. And most of the mess is happening at the superconductor level experimentally, right? So
sorry, what do you mean?
in the sense that the superconducting gap closing and all these properties is where you don't see any unambiguous signatures.
Yeah, I mean, right. So actually, I would say most of the mess is happening actually from the end. We don't have any way to probe the bulk. We're basically probing the end the whole time.
I see.
And so, well, okay, except for, I guess, this measurement here, where I guess here you're probing the bulk, and clearly for this device at least, then this is only one experiment. This device, the bulk is messed up as well because there's barely a gap.
So there is no way to do an STM where you tunnel into the end or something.
Yeah, we have been asking experimentalists this for a long time, and they say yes, maybe, but I think the answer has always been that we haven't seen
But in principle,
a
Ali
result.
Astani's group was doing precisely that, right?
Yeah, true, but there, again, the bulk gap was elusive.
Okay.
Right, so yeah. Okay, so now let me jump in the remaining, I guess, a minute that I have. Let me very quickly tell you what would topological quantum computation look like for these Majoranas. So basically, again, I don't want to spend time going through this text, so let me just point, the figures. So what I have here is 2 Majorana wires, and I imagine that I have measured this pair of Majorana wires, or I've changed it in some way so that this pair of Majoranas are talking to each other and they are gapped out, not really topological. And now, so here actually in these equations, I'm changing the Hamiltonian to make this a little bit non-topological. And so I only have these 2 topological wires with 2 Majoranas. And then what I can do is I can change the Hamiltonian. Let's imagine I can change the Hamiltonian to make this pair non-topological. Effectively, then what I can show is that this Majorana at gamma 2 would have effectively hopped to this position 4. So I can get a Majorana to hop around. And now the important observation was that I don't have to change Hamiltonian. I can just, in a sense, if I can measure this pair of Majoranas, the charge on this pair of Majoranas, that's effectively the same. Because quantum mechanical measurement leads to wave function collapse, I would have effectively changed the state of this system even without changing the Hamiltonian. So I have to do a measurement. And in quantum, for these quantum wires, measurement really means charge detection. So again, this idea, so this is an idea of a Majorana qubit. Okay, I'm really over time at this point. But a pair of Majorana qubits, and here is a measurement of a charge detection. And again, some preliminary data on that. Unfortunately, what happens is that they see, I don't have time, but they see some evidence for, so these dark and bright represent different states of the qubit, different numbers that you can measure using Coulomb blockade. And then when I apply a photon, I can cause transitions between the 2 that are seen. But the coherence time that is estimated from this is picoseconds. So even if Majoranas, we can't be sure because they could be something else. But even if they're Majoranas, they're really bad quality. They live for picoseconds. And what I want to tell you is this scheme of moving things around can be turned into a braiding scheme. So in principle, if one could get this measurement working, then one would have, there is a recipe for making a network of wires and doing braiding that I won't go into. So let me just end. So where are we? So we have a lot of systems now. That's the good news. And they range from, well, generally for quantum computation, they range from the superconducting qubits, which are completely engineered, to quantum Hall, which are like, we wait for topological protection to just fall into our lap. Majorana systems are somewhere in between and showing some preliminary signs of success. We don't, yeah, definitive evidence for any kind of Majorana qubit is not, I wouldn't say that it's in the foreseeable future. We have to wait. And but ultimately, looking back from quantum computation, this whole business is a long haul. we already have some form of quantum computation from superconducting qubits. We barely have we don't have even have a qubit. Well, we have a bit from a Majorana, I guess, but not a qubit. And then we could have, in principle, someday fractional quantum Hall might work too. And we need all these approaches because they all have different advantages and disadvantages, and some could go for some time, and we don't know which one will ultimately work. So thanks for your attention.
Thanks, Jay.
You're welcome. Thanks. Okay. Any questions?
Yeah, so Jay, maybe I will start with question and then I will. So the point is that these Majoranas are not capable of doing universal quantum computation, right?
Oh yeah, sure.
In principle. So in the sense that where do you see this fit in a larger scheme of things? So it's like, can this piggyback on some other system to achieve universal computation, or is how important is to achieve universal computation eventually?
Right. No, that's a great question. So that's why I sort of gave this range from engineered qubits to, let's say, something like fractional quantum Hall or something even more exotic. So you can view Majoranas as somewhere in between in the sense that, so going to topological systems, what we're doing is buying some kind of environmental protection against the environment at the cost of more complexity of the device. This device is definitely more complicated than the superconducting qubit. That being said, actually, these devices are substantially smaller than a superconducting qubit. So if we can, even if our coherence properties become comparable to superconducting qubits for Majoranas, it's still a gain, even if we have to do the same level of error correction, right? So that's already one gain. And the other gain is that, and the other gain is a little bit similar to what are called surface codes that are proposed to be used with superconducting qubits. There also you have a situation where you can do a bunch of Hadamard gates, but you can't do what are called the Toffoli gates or T gates. And for T gates, you need to break the protection from these, in that case, the surface code. And for this system, you have to break topological protection. Now, but on the other hand, as a matter of theory, the threshold, you have a higher error tolerance on that T gate if you have perfect Hadamard gates. So you gain something. And yeah. But ultimately, again, if you get a fractional quantum Hall system, but you still have to do error correction, and I don't remember the estimates now.
Yeah, even FQH, only this Fibonacci anyons have this capability, right?
Exactly, like, only Fibonacci anyons have the capability of universal quantum computation. And actually, one dirty secret of Fibonacci anyons is that no one actually knows how to do quantum operations with them.
Right.
So there isn't even, well, firstly, we don't know if we have Fibonacci's. Maybe we do. The 12th state is Fibonacci, maybe, but we don't even have a scheme for that. But again, and this is why, but this is exactly why I'm talking about the long haul in quantum computation from a broad standpoint, because we so superconducting qubits might be good, okay, for like I don't know, a 15 qubit machine or 20 qubit machine, maybe even a 50 qubit machine or 100 qubit machine. But when you talk about error correction, there's really no scheme where you get actual error corrected quantum computation out of them in any feasible, in any practical looking setup, right? It would look worse than the ENIAC.
I see.
But on the other hand, for Majoranas, because the size is smaller, if you could get a qubit working, then scaling up is actually much easier. But even then, actually, error analysis seems to show that at least if, again, there is a limit here where we're assuming we don't have a quantum computer, so we're just simulating error correction. But what people estimates, we'd still need an insane number of Majorana qubits to actually get, like, let's say, break RSA. That's not really feasible. I don't remember the number, but it is truly insane. So ultimately, like, we might have to wait till a Fibonacci whatever comes along to get like real error corrected quantum computation.
Okay. Okay, I will ask. Jufeng, you had a question.
Yeah, so I think my original question was whether type 1 superconductor is necessary. I think you answered that question. It's not type 2 would work as well, since you brought up that arsenic example. Yeah. Right. Now, I guess it's maybe more of a comment. It seems that to really move forward and make big advances, superconductivity of better superconductors seem to be the catch.
Better superconductors?
Right. For example, if we really have a topological superconductor, or we have a better understanding of a P-wave superconductor, if we actually get one, that would actually lead to major advances in this field. My personal kind of.
No, indeed, I completely agree. That's a very insightful comment, and actually, I do have a bunch to add to it. So, firstly, indeed, looking for, so one of the thrusts in this field is just looking for other unconventional superconductors. So that is definitely, and for that purpose, people are even looking for things that don't have Majorana bound states, that look like something like P-wave. And actually, strontium ruthenate was supposed to be that, and there was a whole
it's a whole kind of worms in that, right?
Yeah, exactly. But now recently, uranium ditelluride has shown up, so there's some hope that something could happen there. But actually, even within conventional superconductors, there is the materials development there is also crucial, because the aluminum that I showed you, so the way back, the first experiment in this material was done with niobium. So the first experiment that was done that I showed you was done with niobium nitride, actually. Niobium tinitride, which according to its inventor, I think it's the Klapwijk, Tune Klapwijk. That's apparently the worst superconductor that anyone has ever made. It's like the most disordered. It's actually somewhere, it's an interesting superconductor from a physics point of view, in the sense that it is somewhere borderline Anderson localized. So it's that disordered, right? And but it had an advantage. It has a huge critical field, and it has got a relatively large TC. So it's a transit. You can work to. It's got a large gap. But then we moved to, but the field moved to aluminum here, because the gap is much cleaner. And so, but the price you pay, but there's at a hefty price. The gap is tiny, and actually the only reason it survives magnetic field is because it's a really thin film, and we don't know exactly how well it survives. Yeah, and why exactly. So and then another dirty secret is actually in this process, Coulomb blockade is actually a very important ingredient for many of these proposals. And the only superconductor till very recently that showed Coulomb blockade was aluminum. It was a strange phenomenon. I mean, what I mean is to show Coulomb blockade, show superconducting Coulomb blockade. Attempted Coulomb blockade experiments. So these were experiments by Mike Tinkham from the 90s. He did it with aluminum to show that Cooper pairs actually have 2e charge and Coulomb blockade is 2e periodic. When the people tried it with any other superconductor, it always came out e-periodic. So there was always some electron somewhere. And only recently there was, I think, 1 or 2 papers, maybe even one, where tin, Chris Palmström and Sergei Frolov, they have shown that tin-coated superconductors can also give 2e periodicity. So there is a lot of materials development, even for conventional superconductors, going into this that is crucial. And that has received very little attention so far, actually.
Thank you, Jay.
Yeah.
Hi, Jay. It's Puyan.
Oh, hi.
Hi, how are
hey,
you?
Puyan. Good
How
to
are
see
you?
you.
Good to see you too.
I was wondering if I would see you. Yeah.
Yeah. So I have a question about your statement about the FESE vortex mode. So you said the percentage. I know that only a percentage shows zero bias peak, but the percentage you were saying was among all the zero bias peaks. How many of them have the conductance quantization or the total vortices?
Oh, no, I think this must be, actually, this is, so this paper that's here, Zhu et al. Okay, this is unfortunately very uninformative. But basically this paper about I think it's called almost nearly quantized conductance in iron superconductor. So this paper, I can send you the link if you can't find it.
Yeah.
But that paper has a histogram, and the histogram, well, is of the zero bias peaks, and so it is out of the small fraction of vortices that show a zero bias peak. So I think ultimately only two vortices showed quantized conductance.
Okay.
They probably started with, I don't know, 50 vortices. Maybe 20 of them showed zero bias peak, and then 2 of those zero bias peaks were quantized.
I see. Yeah.
So yeah, it's an enigma all the way. I'm actually I'm spending some time. Yeah. Mm-hmm.
Right. Yeah. Well, this is quite interesting. I mean, recently I wrote a paper with Pawan actually, and this zero bias peaks. We found a way that the material has natural magnetic atoms in it, the FESET. And we could show that there is actually attraction between atom and vortice.
Well, that's very interesting. Yes.
And if you have enough atoms localized on enough the vortices, it's a ZEEMAN effect that.
I actually, you got cut off a little bit.
Yeah, so I was saying is the ZEEMAN effect of the magnetic atoms, which are localized along the vortex, can kill the Majorana end state if they exist. I can send you a draft if you like.
I mean, I can.
Yeah.
Oh, it's not posted yet. It's not on the archive yet.
It's actually published. It's a PRB.
Oh, it's published. Okay, I'll find it then. Yeah.
Okay.
I can find it. Yeah. But thanks.
And I'm interested.
A quick question related to this. When you say quantized conductance at the vortex, are you talking about a simple magnetic vortex?
No, this is a superconducting vortex.
Right, but it's when you apply a magnetic field, this is type 2, so
correct.
The field penetrates.
Correct.
This is what you're talking about? You're looking at the actual magnetic vortex, looking at the conductance there?
Absolutely,
and,
yes.
But would that simply be because of a pair breaking, like you get 2e squared over h?
Yeah, no, so that's actually a great question. So indeed, so actually, the crucial thing is to avoid pair breaking, and this is actually one. So that's the other miracle that I didn't talk about. You can get some conductance into the vortex. Well, actually, you typically get conductance into a vortex core in STM just because of pair breaking.
Right.
But here we want to not get pair breaking so that we can see the Majorana. So usually, the pair breaking ruins the ability to see the Majorana. So here we're saying, not we, the proposal. This is from Fu and Kane, I guess. That you need a situation where the pair breaking doesn't happen. You just have the Majorana, and then it should go to exactly 2 squared by h.
Puyan, you had a follow-up question?
No. Sorry.
Yeah. So
then you will need actually type 1 superconductor with no penetration of normal.
No. So what happens is this. even in type 1, it doesn't matter. Even in aluminum, you'll get pair breaking if you have a thin film.
If you have
So the only way to avoid pair breaking is to have low dense, what's called a low density superconductor. So Fermi energy and delta have to be comparable. So these iron selenide, iron superconductors, for some strange reason, are close to what would be called in cold atoms the BCS-BC crossover. So they're actually almost like a Bose condensate of Cooper pairs. So when that happens, if you have a vortex, then you can't actually break the pair. Just like in ultra cold atoms, when you apply an effective magnetic field in a Bose condensate, you don't break the bosons up. I mean, you just get a vortex with no pair breaking. So the same situation happens here. It's not quite that extreme, but Fermi, so in this material, Fermi energy is about half of delta or something like that, which is an amazing regime.
Yeah, the problem with this iron, selenide, and selenium superconductor is that, again, it's a material problem, that there's always some excess of iron, no matter how careful you make the sample. So there's always a possibility of a vortex penetration into the impurity iron,
Right.
clusters, and very hard to kind of eliminate that.
Yeah, that's, I guess, what Puyan was partly referring to. Yeah, I have to look at this. I mean, the claim from these experimentalists is that they do a lot of annealing to get rid of excess iron. So
I'm not
I
sure.
don't know to what extent you can actually,
it cannot be completely eliminated no matter how careful you are.
Right. I guess they can get rid of it from the surface because they can.
Sometimes you can see if there's a big cluster, but what I'm more worried about, if it's a small enough cluster, you can't even tell that if there's a few iron clusters.
Well,
actually, you're right that the surface can be cleaned, but actually the mechanism we talk about, it cares about the bulk iron atoms. That will kill the Majorana at the end of the vortex. It's related to that work I did with Ashwin on relationship of the edge Majorana and bulk superconducting state.
Right.
So,
No, I see that. I mean, I can kind of see it. I mean, actually, a bigger issue would be so again, I'm still trying to, I'm thinking about these platforms seriously, and maybe this is the central issue. Maybe that is the answer to why Majoranas are not present in many of these cases. But in addition, if you have these iron clusters, that would be really bad news, because they'll probably kill superconductivity around the iron cluster.
Absolutely right.
Right. And
polarized, polarized there.
Well, actually, in the picture we have, Jay, it's you change the type of superconductivity around the iron atoms. You make it more of a spin triplet.
Yeah, you might get the triplet S equal to 1 superconductivity, which by itself could be interesting, right? I mean that, but it's not going to be P wave.
Well, but even in that case, there will be a domain wall, and that will be gapless. But the point is, and the point is, any gaplessness is very bad news for Majorana. So, okay, thanks. That's actually very, very helpful.